Now that we have the definition of sheaf cohomology, let's look at some basic properties. So we're looking at a quasi-coherent sheaf of modules on a variety X over an algebraically closed field. First, the zeroth cohomology corresponds to the global sections. Why is that? Well, if we look at the Czech complex, it starts with C0, goes via D0 to C1, and so on. And so, since there is no image, the image is trivial, of this map, the zeroth cohomology is the kernel of D0. So what is this? Well, if we take a cover, an open cover, U1 to UR, then any phi in C0 of M, this is a collection of R maps where phi I is in M of UI, because I need intersections of 0 plus 1 members of my open cover. So what does D0 to phi do? Well, in the part indexed by ij, this is phi I minus phi j restricted to the intersection of ui uj, because here I want to look at all such intersections. These are what index my, these are what constitute my summons here. But what does this mean? This means that the kernel of D0 consists of all local sections, phi 1 to phi r, that agree on intersections, because for the kernel, I want this to be 0. So I want phi I to be equal to phi j on the intersection. And this is exactly the sheaf property for global sections. So this means that these phi I to phi j come from something global. So phi defines a global section. And this is precisely what it is. So therefore, the condition that something belongs to the kernel of D0 is exactly the condition that it is defined globally. Next, if X is affine, then all its cohomologies, except for possibly the 0 part, vanish. We'll prove this assuming what we have already proved, or rather what we have already assumed to be proved, namely that the cohomology is independent of the open cover. In reality, you prove this first, and then you prove independence of open cover starting from that. But having the open cover independence done, we can prove this in a very short step. Simply observe that we can cover X by itself. So Cp of xm is going to be 0 if P is greater than 0. Because when we create this, we need to take intersections of P plus 1 members of our cover. But since the cover only has one member, this is possible only for P equals 0. So this implies our result. For projective varieties, we also have a vanishing, starting not from 0 in general, but from the dimension of X. So here X is projective of some dimension n. So how do we do this? Well, there are polynomials, homogeneous polynomials, f0 to fn, such that the vanishing of these polynomials altogether doesn't happen on X. Not all of them vanish at the same time on X. The reason for this is something we had when we discussed dimension a long time ago, that if you start with a variety and then you look at the zeros of one polynomial, you reduce the dimension by 1. So if you look at the zeros of n plus 1 polynomials, you reduce the dimension by n plus 1. And since the dimension is n, this cannot happen. So therefore, you have an empty set. I mean, of course, this doesn't hold for any polynomial, but there exists. You can choose them successively, starting with f0. So this means that we get an open cover, u0 to un, where ui is x outside the vanishing set of fi. So we have an open cover with n plus 1 elements, and as in the previous case, we conclude that if we need to choose more members, so starting from n plus 1, we will get Cp of m to be trivial, and therefore the cohomology will vanish starting then. Finally, if we have a closed embedding, so if x is a closed subvariety of a variety y, then their cohomologies agree in the sense that the cohomology on y of the push forward of m is the same as the cohomology of x of m on x for all p. The reason for this is that if I have u1 to ur an open cover of y, then I can take as open cover of xn, or of x intersection u1 to x intersection ur. Now what I need to compare is the values of m, which is my sheaf over x, at these x intersections of these open covers, but that by definition is the same as the push forward of m evaluated at such intersections uj, by definition of the push forward. And now this gives me my Cp of n, and this gives me the Cp of the push forward. And because, I mean, these are constructed from those in exactly the same way as these are constructed from those, I get the same cohomology. I leave it to you to check that the co-boundary maps, the dp, behave well with respect to this construction, so I get the same cohomology on either side. Next is the long exact sequence in cohomology. So if you take a variety x and an exact sequence of quasi-coherent sheaves, then as in all reasonable cohomology theories, you get a long exact sequence of cohomology. I will give you a sketch of the proof. So if we start with, in the first row, this CPM1, CPM2, CPM3, and do the same thing for CP plus 1. And here we have the co-boundary maps that I denote by dp all of them, even though they really come from 3 different complexes. Now my claim is that the rows are exact. So for the rows, I am looking at, for example, here, M1 of these uj that are affine. But M1 is quasi-coherent. So M1 of uj, this is going to be the same as taking the restriction of M1 to uj and applying it to uj. So in other words, this comes from some module n. It's the sheaf associated to a module via this tilde construction that we had before. And these, so this m tilde will be the restriction of m1 to this uj. And so these are global sections of this m tilde, but global sections of m tilde, this is just m. And I do the same here and here. And then I end up with exactness of global sections. And, or exactness of, so I get exactness of these modules, and so I have exactness. And the same down here, and this commutes, these squares commute. And so by the snake lemma that you know from courses in homological algebra, you get a long exact sequence from this. I will skip the details of that. So what does this long exact sequence mean? There are a few places where we can stop and think about this. So remember that I advertised cohomology as a way to fill in the lack of exactness when we take global sections. Indeed, this is relevant here because we have proved that this is the global sections of M1, global sections of M2, global sections of M3. And so I do not in general have exactness, but the cohomology sequence starting from H1 gives me all the details. Now, if X is affine, then I do get an exact sequence globally. This can be proved without resorting to cohomology. With cohomology, it is just the statement that H1 vanishes, which we have seen that it does for affine varieties. And the non-cohomology proof of this is simply that if X is affine, is spec R, then each Mi is Mi tilde for a module, an R module Mi. And we know that such sheaves are exact if and only a sequence of such sheaves is exact if and only if the corresponding sequence of modules is. And the modules are precisely then the global sections. So this means that we do have exactness on global sections. Also, remember that one of the things that we have, this failure of exactness on global sections, means that if you have a map of sheaves that is surjective as a map of sheaf, meaning that its image sheaf is exactly the target, then you do not necessarily have surjectivity globally. This we saw in the previous part of the lecture. But if the map is injective, this is the case. If the map is injective, an injective map from M2 to M3 corresponds to an exact sequence where M1 is 0. If now this map is also surjective, this means I have an exact sequence here. So if I take global sections, I replace this 0 with H1 of X M1. But M1 is 0, so this will vanish. So I do in fact have exactness on global sections. Again, you don't need cohomology to prove this, but this aligns with that idea. That surjectivity is problematic only in the absence of injectivity. Finally, all this shows that it is really the H1 that is the most important. H1 and its dimension little h1 measure failure of exactness or surjectivity or what it is you are interested in. There are cohomology theories that only define H1 and do not go on continuing with H2 and so on. Our cohomology theory does go on, but the thing we care about the most in general are these H1, if we are to characterize lack of exactness. Let us now, as an example, look at the cohomology of these twisting sheaves. They are all over the place because they arise as, well, many sheaves turn out to be isomorphic to these twisting sheaves on projective space. So if you have M, the direct sum of these OP and D, overall D graded by D. So this is just saying I am looking at all these twisting sheaves at once and keep track of the D. Then the following are isomorphisms of graded vector spaces. We'll see what that means in a minute. So on the level of zeroth cohomology, the zeroth cohomology over Pn of this sheaf is isomorphic as a graded k-vector space of the polynomial ring to the polynomial ring in n+1 variables. This statement just means that if I look at degree D, so my cohomology respects this direct sums, if I look at degree D, then this is isomorphic to the degree D part of this polynomial ring. And I mean, this is exactly OPND of all of Pn. So then it's clear that this commutes with the grading. I mean, this is the D part of N, of the corresponding thing for N. And the fact that the global sections of the twisting sheaf are exactly the degree D elements here, this is something that we know. We have seen that before. So this holds. Next, the nth cohomology is also the polynomial ring, but with a different grading. So to adjust the grading, we call the variables t0 inverse to tn inverse and multiply by t0 product with all other ti's inverse. So why is that? Well, if we compute this, I leave the computation out, but if you compute the nth part, you will see that this is the sum over all I of the polynomial ring localized at t0 to everything except ti. And Cn+1 of M is the polynomial ring localized at everything. So now the nth cohomology is obtained in the following way. So since Cn+2 of M is 0, as we have seen, because we're over the projective space, this is all of Cn+1 modulo the image of Dn. And if you look closely, all of Cn+1, this comes from this localization. So this is the span of products t0 to k0 up to tn to kn, where the ki are integers. The thing you are modding out with is the same, save for the requirement that there is one ki that is non-negative. So the quotient is the span of all products like this, where all ki are negative. And this is exactly the meaning of this object. Finally, having dealt with the bottom and top cases, for all other P, the Pth cohomology vanishes. This is proved by induction. The base case, induction on n, the base case n equals 1 is void, so it's trivial. And in the general case, you use the long exact sequence of cohomology for the inclusion of Pn minus 1 into Pn. I will omit the proof. By looking carefully at the degrees and tracing them one by one, you get as a corollary that the dimension little hp of Pn of OPND is as follows. It is non-zero only if P is equal to 0 and D is non-negative, in which case it is n plus D choose n. Or if P is equal to n and D is at most minus n minus 1, in which case minus D minus 1 is greater than n and minus D minus 1 choose n is this dimension. Otherwise it is 0. Before we finish this part, I want to address duality. So if you have seen other cohomology theories, you might expect some duality hold. And indeed, there is a duality in the case where you look at the cohomology of locally free sheaves of finite rank on a smooth irreducible projective variety of dimension n. Then, Serre duality asserts that the canonical line bundle omega x satisfies hp of xn, so the dimension of the Pth cohomology, is equal to the dimension of the n minus Pth cohomology of x, with the sheaf being the dual of m tensored with this bundle omega x. This canonical bundle is the exterior product, if you're familiar with it, with the cotangent bundle. If you're not familiar, this is an important bundle that is canonically defined and that plays this role, that exists and plays this role of dualizing this. It is an understatement to say that this is a deep theorem with a difficult proof that is outside the scope of this course, but it is an important one and a useful one for proving lots of other things. And it is due to Jean-Pierre Serre. So we know that we have duality for cohomology in these nice cases.